Science on surfaces. A bigger perspective on the small.
So welcome to this first episode of this podcast, Science on Surfaces, a bigger perspective on the small, where we will zoom in on science that impacts our everyday lives. So my name is Malin Edvardsson, and at my side here in the studio I have a renowned scientist, Professor Bengt Kasemo. So you are a professor of physics at Chalmers University of Technology, and you're also a member of the Royal Swedish Academy of Science and the Royal Swedish Academy of Engineering Science. Welcome.
Thank you very much.
So you have a long experience in surface science, and you also work with nanosafety, and you work with sustainable energy and the future energy systems, and also climate change issues, right?
That's right.
So let's start with an introduction to the core topic of this podcast, which is surface science, or actually even a bit broader, science on surfaces. So here we will address science where surfaces are related in one way or the other. So strictly speaking, surface science is the study of phenomena at interfaces. And this is something which we address in our surface science blog post series on the Biolin Scientific website. But here in this pod, we will take a more broader or zoomed out perspective and talk about phenomena on surfaces and interfaces in general. So let's start with the definition of a surface. What is a surface, would you say?
A surface is an interruption of matter, which we usually call the bulk of the matter, and then there is an interruption. So if we take a piece of copper and we break it in two pieces, we make two surfaces. Or even more correctly, we make two interfaces, because the surface of the copper is in air, so it's an interface between the copper and the air.
Yeah.
If you break it underwater, it's a metal water interface that we create, and so on.
And so on. So that is, in the simplest case, sort of the definition of a surface. Mm-hmm. But then we have, we are basically surrounded by surfaces. So a surface can be much more than a pure element, right?
That's right. We have very complex surfaces around us. We have the leaves of trees. We have the wings of a butterfly. We have the road surface that we drive on. And we have the surfaces inside our body between, for example, our joints. In the hip, we have a ball and a cavity.
Yeah.
And there is an interface between the cartilage of the bone or the joint. Mm. And the synovial liquid, that is the lubricant liquid of the joint. Mm. So we go from everything from single element surfaces to very complex biological surfaces.
Mm. And also what you mentioned here is actually that we have natural surfaces and we have man-made surfaces.
Mm-hmm. That's right. And man-made, a very good example of a man-made surface is our sink in the kitchen.
Yeah.
For example, we are used to the sink being always stainless. But that's a very advanced artificial surface. The main component is iron, but then there is chromium, molybdenum, and it forms a corrosion-resistant surface, an oxide. And we use that every day. We have in the house the windows, which we unfortunately have to clean, unless we make them self-cleaning, which is a small step on the way.
Yeah. And then you actually have another surface on a surface if you make them self-cleaning, right?
That's right. You have a nanostructured surface on the surface of the normal glass to make it self-cleaning through rain and sunshine and so on. Mm.
So we have the definition of a surface, and basically we have concluded that they are all around us, that they can be both natural and man-made. But then we come to the question science on surfaces, and the kind of science that we are referring to. So what could that be?
Well, that could be anything that happens on a surface. A surface is never static or very seldom static. If we hide the surface in vacuum, we take away everything, all air molecules and so on, then it can be static. But as soon as we let some air in or some liquid to the surface, things start to happen. The surface atoms react, they form new compounds, like when the stainless steel sink is formed. During the formation, the ion and the alloy components like chromium, molybdenum meet air and water vapor and form oxides, complex oxides. And that's what we call oxidation. And if it doesn't stop with the oxide, it's what we call corrosion. And it just goes on and on and on. But it could also be what happens in our catalytic converter, catalytic cleaner of the gases that come out from a combustion engine. These are small particles that are noble metals very often, and they can clean the toxic or unwanted components of the exhaust gases, like carbon monoxide, like nitric oxide, like unburnt hydrocarbons and so on. And that's an area called catalysis.
So that is a process taking place at the surface.
That's taking place at the surface.
But is the surface also involved, or is it just like a mediator?
The surface is highly involved. In the corrosion example, of course, it's the surface itself that changes. In total contrast to that is the catalyst surface, which by the high school definition of a catalyst is that it doesn't change. But the catalyst changes what comes onto the surface. So it makes, for example, carbon monoxide molecules to be carbon dioxide molecules. It makes nitric oxides to reduce to nitrogen and so on. The catalyst itself does the job, but it doesn't change, ideally.
So when did we start to get interested in what happens at surfaces?
I think it happened already in my undergraduate studies. I was in an environment that was very, very strong in solid state physics, in material science. And at that time, people who did the science of solids, the solids on materials, started to be interested in the material surface itself. So I was in some way influenced by that global trend that started at that time, or had just started, to understand what happens on surfaces. So that became a topic for my PhD studies.
And so a global trend. Why was there a global trend?
It was a global trend for two reasons. One was purely scientific and one was technological. The purely scientific reason was that people thought they started to understand the bulk of a material, the inner of a material. And they saw there was a challenge at the surface, because then the periodic structure of the inner part was broken, and things behave differently at surfaces than in the bulk. So that was a scientific drive. But the real driver, the real pusher of the whole field was the development of semiconductor technology. The invention of the transistor, that was is usually referred to as 1947, and the Nobel Prize a few years later. The first integrated circuit was awarded also the Nobel Prize from a discovery in 1959. And integrated circuits, semiconductor technology, and the making of solid-state transistors involved enormous amounts of surface science in all steps, in all production steps. Another driver was material science, to make materials better at the surface, to make them more functional.
So what kind of materials are you referring to?
I could refer, for example, to alloys like the zinc. We talked about stainless steel.
Yeah.
Because industry demanded very different types of stainless steels other than in the zinc. For example, stainless steel working at much higher temperature or in tougher environment. But it could also be ceramics. It could be materials in the car engine, the piston ring and the cylinder wall at higher and higher speeds of the engine, rounds per minute.
And higher temperatures.
And higher temperatures demanded new engine materials. These are just two examples.
Yeah. And also I'm thinking about like biomaterials, which I think goes back even further, but which is like a different category.
Biomaterials, in a way, in material science, it came in later. I would say that there were some examples in the 1950s, but maybe in the 1960s and especially in the 1970s, people in medicine started to realize that some lost functions of the body could be repaired by artificial materials called implants. And I happened to, more or less accidentally, to be dragged into that field through a surgeon in Gothenburg, Per-Ingvar Branemark. He had developed or invented a dental implant. And he asked me to help the team with the material science aspects on the surfaces. So that's how my interest there started. But in parallel, there were many other developments like artificial knees, joints, artificial blood vessels, later on stents for coronary arteries in hearts and so on. Endless number of examples from plastics to metallics to ceramics.
So here we have, we're touching upon actually impact on our everyday lives. So you've mentioned cars, you've mentioned implants, the zinc, and these are objects, maybe not implants. It's not like not everyone has an implant, but cars and the zinc is something that we interact with more or less every day.
And semiconductor devices.
Yes, definitely. And so this is a scientific area that is very much relevant to all of us and impacting our everyday lives. So do you have any additional examples of relevant inventions or science that has...
A very large area that we haven't touched upon is the surfaces, how they look. That is what we would call in science optical properties of surfaces. Because it's the optical properties that decide what they look like. And that area can range from aesthetics, how aesthetic are surfaces, how are they getting different colors. And there are many ways a surface can get different colors. One is by interference, and that is what we see in a soap bubble. A soap bubble with its many different colors is an interference of the incident light.
Which, just briefly or quickly in a sentence or two, what does that mean?
What interference means is that the wave, the light waves that hit the surface can either amplify itself at a certain color, or it can extinguish itself at other colors. And the amplified colors get the colors you see, and the extinguished colors are disappearing. So from white light, if blue disappears, the soap bubble look red, and vice versa.
So the surface properties determine basically the color.
Right.
That's what you're saying.
But there are other ways the color can be determined, and that is not by interference, but by absorption, sucking up certain parts of the light spectrum. If you suck up the blue, it looks red, and vice versa.
Right. So that's what we have in leaves.
That's what we have in leaves, and there are still there are also combinations of interference, scattering, which is just reflecting, and
which is actually why the sky is blue, right?
That's right. That's right. That's a combination of mainly a scattering event.
Yeah.
Maybe we don't go into that in detail,
no.
But it's a very good question. Why is the sky blue? But these different events, reflection, scattering, absorption, and so on, can give fantastic color variations like the wing of a butterfly, also without going into details.
So the surface properties determine the colors and, of course, many of the other behaviors that you have already mentioned. And I'm thinking about how you characterize these properties, or how you can, because you're talking about like a very small scale. I don't even know exactly what length scales we're talking about here.
We're talking typically about the length scale from the most conservative definition of a surface is the one atomic layer.
Yes.
It is the outermost. When we broke, as an example, broke the copper piece, we have one outer atomic layer of copper atoms if it's in vacuum and it doesn't react with air. And one atomic layer, that's about a few angstrom, a few tenths of a nanometer. So it's very, very, it's atomic size.
Yeah.
But if we move, for example, to light and to low energy electrons and other particles like ions, they can penetrate a bit into the surface. And to make a less conservative definition of a surface, it's up to, say, 100 nanometer. That's still a fraction of a micrometer.
Yes.
So we have to divide a micrometer into 100 pieces to get to what we really call the surface.
Yeah, and I was thinking as a reference to that length scale, I read somewhere that the diameter of a strand of hair, like a blonde hair like mine, is like 50 micrometers.
Yeah, so it's a very bulky thing for. So the hair itself has a surface that is very thin compared to its thickness.
Yeah, exactly.
Sometimes we also say that the surface depth could be defined as the wavelength of light, and that's correct in some cases, because for a non-transparent surface like copper or gold that doesn't let the light through, it penetrates typically a distance which is its wavelength.
Okay.
1 or a few hundred angstrom. Then it's extinguished. But on the other hand, in glass, the light goes straight through. And there are no surface effects except at the very surface. The interference pattern I talked about, if there is some variation in the composition of the glass into the surface, it can give rise to interference patterns and so on. We're again talking about a few hundred nanometers.
I think some wavelengths don't pass through glass.
Some wavelengths don't pass
But
through light.
they're the wavelengths that we see.
Right. For example, it's pretty well known that if you sit behind a normal house window, you don't get a sun tan.
Yes.
And that's because the UV part, ultraviolet part, the shortest wavelength part of the sunlight that gives us a tan, is actually absorbed in the glass. It's sucked up by the glass. And also on the other side of the wavelength spectrum. If you go, red goes through, but some infrared light doesn't go through. So the heat radiation doesn't go through.
Yeah.
If you go sufficiently far into the long wavelength.
Yeah. So we're talking about these really tiny length scales, and what are the challenges of measuring these surface-related phenomena that we are talking about here in surface science?
That's a very good question, because as surface science developed, it did so by the development of a large number of new methods. It turned out that if you just switch from solid state science to surface science, we will be very handicapped or limited in our ways of looking at surfaces, because the tools were not there. So when the almost explosive development of surface science began in the 1960s, extending into the 70s, it was very much through the development of new tools. So when I started, the area was very tool or method oriented, and new tools came every few years and made it simpler and simpler to follow what happens on surfaces. And since surface science and surface technology were technologically very important, it gave birth to a whole new industry focusing on surface science methods, which you are very well aware of.
Yeah. Okay. So, I mean, I think it's very fascinating that you can then, with these tools, you can study phenomena that you can't really see with your own eyes. Like, for example, you mentioned the oxidation, a car rusting. So basically we can study that process before we can see it. I mean, we can see it when the car paint starts falling off. But with these tools, you can study that process already before we can see it with our bare eyes.
That's right. So what you do typically is two types of studies. One is that you take the real material in the real situation, like in the car engine or in the sink, and you let it be there for a very short time, and then you take off a piece and you look at it with some good methods, and then you wait another day and you take a new sample 10 days later, a month later, a year later, and you follow the development of the surface over time in its real environment. But you also, as an alternative or a complementary method, I should say, you do this in the lab. So you design a reactor that is quite mimicking the real situation well, but with much more control. And there you can also include some measurement methods that look at the surface all the time. So you have a real-time monitoring of the surface and how it evolves over time.
So this is like a model system of the real...
This is like a model system of the real system, and they complement each other.
Yeah, that's interesting. So what fascinates you the most with this area?
What fascinates me most is how broad and versatile it is, how a basic platform of knowledge and methodology, and I should also say theory, how a basic platform, or quoting Richard Feynman, to have a toolbox for general surface studies. It brings you into extremely diverse fields, and I think my own career is a good example of that. It started as essentially the solid state physics of surfaces, the purely scientific part. And then it moved into catalysis, and then it moved into biomaterials. So when I told people later in my career, I was working on car exhaust catalyst with Volvo and with dental implants with an implant company. They asked, how can you do that? So diverse things. And the answer is because it's a common knowledge base, a common instrumentation base. And then you can jump into many different areas.
All related to surfaces.
All related to surfaces. So I think that's what is most fascinating, that you can, like going into energy and climate and environment. It's also a natural extension because the climate technology or climate phenomena, the energy technology, the environmental technologies are all full of surfaces in their methods for analysis or in their methods for performing functions like electric vehicle or reducing carbon dioxide emissions by capturing which is called carbon capturing and
where
storage.
You need a surface to capture.
You use the surface to capture the carbon dioxide.
Yes, exactly. And the same goes with the nano safety.
It's the same, and it's a very maybe that's also one of the more interesting aspects of surface science, that the development of nanoscience and nanotechnology and the development of surface science marry together two very intensive fields. Because if you think about it, you take a particle that is like micrometer, like the thickness of the hair, and you shrink it. The more you shrink it, a ball or a cylinder, the more surface is there. So when the ball or the hair is like 10 nanometer, it's almost all surface.
Yes, in relation to the volume.
In relation to the volume. And if you count the atoms, if you're down to 1 nanometer, they are almost all surface atoms.
So looking at nanoparticles, for example, it's basically all surface.
It's a lot of surface for the smallest particles.
Yeah, so surface properties are important.
Again, the definition of nanoscience is usually said it's entities, bodies that are between 1 nanometer and 100 nanometer. And if you remember, that's the size I said is the range of a surface, how thick it is. So in surface there is one dimension that is 1 to 100 nanometer. For a nanoparticle, there is 3 dimensions, or sometimes 2 dimensions because it could be a fiber. But 2 or 3 dimensions in nanotechnology are the same length scale as surface science.
So, yeah. Anything else that you're thinking of that is relevant to discuss?
I think there are lots to discuss, but I think what we have talked about gives the flavor of what surface science. Maybe I should, maybe if some theoretically oriented people are listening, they may be disappointed because I haven't mentioned the word theory.
Right.
But in the same way as development of new scientific instruments and methods were important for the development of science on surfaces, theory development was equally important. So it's really a triplet of doing experiments, developing methods, and developing theories that moved surface science to where it is today.
And it will continue, I assume.
It will continue, and it continues in the traditional way as the scientific field develops. One is that for the simplest surfaces, like a copper surface, which is very simple comparatively, or a copper surface with a carbon monoxide molecule, there will be a very deep digging refinement of our knowledge to know almost everything about that complex system. And at the other end of the spectrum, surface science will attack more and more complex surfaces, more and more compound surfaces, where the same methods and theories and so on that apply to the copper surface with carbon monoxide are not enough. So you need new methods to attack those more complex surfaces.
Right, because you mentioned that we often use model systems and we are surrounded by so many complex surfaces.
And the very complex surfaces create a challenge that we need to simplify the interaction to understand anything. So if we take, for example, blood in the body, meeting the inside of an artificial blood vessel, it's an extremely complex situation with a lot of molecules in the blood and a lot of complex molecules on the surface of the implant. And sometimes we need, or continuously we need as a complement, to look at how the full implant works in a living body. We also need to look at how the plasma of blood works with the same implant. We may even want to look at a single type of proteins, how they interact. And then we make an integration between the full complexity and the simplest approximation.
And then we can map out and understand.
What goes on in the real world and how we should or could improve the implant.
Thank you. So, I think that's all we had for today. We've covered surfaces, where we find them, the kind of science that you're doing on surfaces. So thanks for listening to this first episode on Science on Surfaces, a bigger perspective on the small, with me, Malin Edvardsson, and Bengt Kasemo, Professor of Physics at Chalmers University of Technology. Thank you.
Thank you very much.